Welcome to Lesson 1C, Ideal Gas Mixtures. Let's consider an ideal gas mixture where we have a tank, as I show here, with various species in them, air plus some pollutants. These are all gases. In fact, we'll assume they're all ideal gases, which makes our algebra easier. And in this class, we'll consider only ideal gases. We have a given temperature and pressure and volume. That's the bulk properties of this tank or container. And then it has J, capital J, number of species, and then each of those has a subscript little j. So if you have three gases, you would have J equal 1, 2, and 3. Each one of the species has a mass, has a number of moles, and then we'll also define the total mass, total number of moles. And then we'll define these partial pressure, partial volume, mole fraction, etc. for the various components of this gas mixture. So our assumptions are ideal gases and all gases are well mixed. All that means, we'll use this a lot in this course, that means if I take a reading here or here or here or here, anywhere in the tank, it'll give me the exact same properties of the air at that location. So there's no variation in space of these air pollutants. So what we'll do is write equations for conversions of mass fraction, mole fraction, partial pressure, etc., and define all these things. First, we write the total mass, and I show three different ways to write this. And so you can write, to be mathematically correct here, it's sum of J equal 1 to capital J mj. Remember, J is the total number and little j is the index. So mt is this. We can be a little bit lazy and just put a j, knowing that we are just summing over j for however many j's there are. Or we can get real lazy and just do this, which also implies we're summing over j. I'll do all three of these depending on my mood. And then similarly, you can do the same thing with the total number of moles. All right, so now let's define a few other things. So first, let's define mass fraction. So as its name implies, it's the fraction of mass. So this would be of species j. And we'll give that the symbol f. So f sub j is equal to the fraction, or the mass fraction, which will be mj over mt. And so that's one of our fundamental equations here. This f is dimensionless. So our curly brackets, remember, dimensions of is 1, or dimensionless. The units, square brackets, of fj is also 1. It's unitless, but we typically have very small amount of air pollutants. So if we have some air pollutant like carbon monoxide mixed with air, sometimes we'll talk about microgram per kilogram, or possibly milligram per kilogram, etc. So it's two mass units on top of each other, which is dimensionless, but the numbers can change depending on these kind of units. These are fake units really, because it's dimensionless. Similarly, let's define something called a mole fraction, and that's, again, of species j. We'll use the notation yj equal nj over nt. So it's, again, just like this mass fraction was defined, it's the number of moles of j over the total number of moles. And again, keeping consistent with how I like to always do units and dimensions, the dimensions of yj are 1, it's unitless, dimensionless rather, and then the units of yj are also 1, or people like to do parts per million, since these are typically very small numbers, or very, very small numbers, parts per billion, ppb. So for example, we might have yj equal 4.1 ppm of some contaminant like carbon monoxide. So suppose we have that. What does that mean? In an equation, use yj equal 4.1 times 10 to the minus 6. So ppm, this is parts per million. And if you have parts per million, to get the actual yj, this is a very small concentration, by the way. Yj is only 4.1 times 10 to the minus 6 because of the million. And that's the actual number. So you would use this number in calculations with yj. When you have some kind of equation with the yj, that's what you would use. So we can say if yj equal 4.1 parts per million, that's also equal to 4,100 parts per billion of CO. And to go from parts per billion, you would take 4100 times 10 to the minus ninth, since it's billion. And if you do the math, that's also equal to, well, 4.1 times 10 to the minus sixth. Or if you want to write it out, 0.5041. So you want to use this number or this number in your calculations. I want to make a quick comment about bias, and you'll notice bias in reports, company brochures, in the media. It's really bad sometimes where they have bias. So which sounds more alarming to the average person on the street? Can say it this way: the mole fraction of CO in this very clean air is only 0.0000 with 5 zeros, 41. So that looks like a really small number, and they say this very clean air. So this is someone who wants to say that this air is not very polluted. And I keep getting worse and worse here. This clean air has only 4.1 molecules of CO per million molecules of air. These are all identical statements. They're just stated differently, which shows the bias of the person writing them. I want you to pay particular attention to this throughout the semester. This is very important when we talk about air pollution. You can say this air has 4.1 ppm of CO. That's probably the most neutral statement there. This air has 4,100 parts per billion of CO. So you make a bigger number. Instead of giving this little number, you make a big number. Even though they're the exact same concentration, this one looks worse. This air is polluted with 4,100 ppb of air, CO. So again, it's a little more like severe, like people, oh, this is bad. And then this is the worst one. This toxic air has 4,100 ppb of deadly carbon monoxide air pollution. Hopefully you can see in this little example the bias and how different it looks between here and here. So keep that in mind as you're reading stuff. Okay, I want to talk about Amagat's law of additive volumes. So here's the definition. Again, we have a mixture of gases in a container like we sketched. And Amagat's law says that the partial volume, Vj, again, I use that symbol in my notation when I write with pencil or pen, it's Vj with a bar, but in my typed notes, I use this Arial font instead of the Times Roman to distinguish this V from this V for volume. So you'll see that I do that consistently, hopefully. What is partial volume? It's the volume that species J would occupy if it were the only gas in the container at the same pressure and temperature of the actual bulk gas. So Amagat's law in variables says that the volume, this is the bulk or total volume, is equal to the sum over all the species in the tank of Vj. So that's what Amagat is saying. So it's kind of similar to mass. The total mass is the sum of all the masses of each species, while the total volume is the sum of all the partial volumes of each species. So I like to do thought experiments, and that simply means let's think about this logically. So let's do the actual tank, and let's think about our thought experiment. And so these are the same thing, but here's my actual tank, and it has some NT, some MT, total number of moles, total mass, volume, pressure, temperature, etc. But suppose we have two gases, and they can be air and something else, something like carbon monoxide, like my example. Let's suppose that this much of the volume is air, and this much is carbon monoxide. By the way, generally we use 1 for the air. You don't have to do that, but V1 is V air. We also can just put the actual element name or molecule name instead of the J, so we don't have to remember which one is 1 and which one is 2. So I would call that V1, partial volume of air, and this would be the partial volume V2 or VCO. And so in this thought experiment, we have this mixture of gases, but suppose you can separate these two gases into the CO and the air. And so the volume that the air occupies is the partial volume of the air. The partial volume that the CO occupies is the partial volume of the CO. And these are at the same P and T as before. And it's the same total volume. So these are the same as the previous actual tank. So by definition, it's the volume that species J would occupy if it were the only gas in the container. If I suddenly slid some kind of a barrier between the air and the CO, suddenly I have this air, and that's the volume of that air that occupies at the same pressure and temperature of the original tank. So what Amagat says, that V air plus V CO equal V. And generally you can put a T there, V total, but I'll just use V as the bulk or the total volume. We also know the ideal gas law, which is in this form, PV equal NT RUT. Well, it turns out that either the air or the CO in this case is also an ideal gas. So for each species, we can write a similar ideal gas law. For a species J, this same ideal gas law applies, but in terms of partial volumes. So PV1 equal N1 RUT, or PV2 equal N2 RUT, where 1 is the air and CO is the carbon monoxide in this case. And so in general, for species J, we can write PVJ equal NJ RUT. So this is the ideal gas law in terms of partial volumes. Remember, NJ is the number of moles of species J. So we have the same looking ideal gas law, except it's in terms of just one of these species. And physically, I can say, if I had this barrier and think of this as just a tank of air, of course the ideal gas law works for it, and its volume is VJ or V1. So the ideal gas law certainly has to work. And same thing with the CO. Consider that a tank by itself if there was some kind of barrier in here in our thought experiment, and you can prove to yourself that that works. Okay, there's something very similar called Dalton's law of additive pressures. We define partial pressure instead of partial volume, pressure that species J would exert on the walls if it were the only gas in the container at the same volume and temperature of the actual bulk gas mixture. So that is our Dalton's law, which is very similar to Amagat, except now we're dealing with partial pressures instead of partial volumes. So we can write Dalton's law mathematically as total pressure is sigma J equal 1 to capital J of all the partial pressures. So all these pressures add up to the total pressure. So let's do a similar thought experiment. So I'll do the same thing. This is the actual, and then I'll have the thought experiment here like I did before. And I think I forgot to put an equal sign. So this is really the same thing. It's just expressed a different way. But now I'm going to make the actual tank. Again, we have some total mass, some pressure, some temperature, some volume, some total number of moles of molecules. And that's equal in our thought experiment to this. Again, if there's only two gases, take the same air and carbon monoxide as our example. So now we have the same volume, V, but we're splitting it into two parts. So suppose we magically remove all the CO and there's only air. So this would be J equal 1. This is the air only, and P equal P1. It's the same V, and this may get colder or something if thermodynamically we remove some gas out of it. It'll tend to get colder and pressure would go down, but we have the same volume and the same temperature, but we have a different pressure. We have a lower pressure because we have not all the gas in here, we have only air. And then here J equal 2 is the CO only, so P is equal to P2, or the P of the carbon monoxide. And again, this is the same V and the same T as the original case. Same volume, so just imagine we take all the CO out, all we have left is air. It's going to be a lower pressure, of course. The second tank is filled with CO only. That's all the CO that we remove. Put it in another identical tank, make sure the volume and the temperature are the same, and that is the partial pressure of the CO. So again, we can do an ideal gas relationship for the total PV equal NT RUT. But now here we can write this one as P1V equal N1 RUT, and write this one as P2V equal N2 RUT. So for species J, in general, PJV equal NJ RUT. So that is ideal gas law in terms of partial pressures due to Dalton's law. Now let's look at the relationship between these variables, between mole fraction, partial pressure, partial volume. So I'm going to start with PV equal NT RUT. That's the ideal gas law for the bulk. And I'm going to write this as P equal NJ RUT over V. And for partial pressure, PJV V equal NJ RUT. That's the equation I just had up here. So I know the total ideal gas law and this ideal gas law just for that partial species, that one species in there. So I solve for PJ, same way, NJ RUT, and I just noticed the mistake. This is NT. I don't know if I said that or just wrote it wrong, but that's NT RUT. This one is NJ RUT over V. And so let's combine these two into a ratio. So PJ over P is equal to NJ RUT over V divided by NT RUT over V. And notice that this cluster cancels with that cluster. And so this is equal to NJ over NT. And what is that? That's how we define Yj as the mole fraction. So before I write the final equation, similarly, so we did this with Dalton's law. If you use Amagat's law in terms of partial volumes instead of partial pressures in this equation, so you use this equation plus another one, and you could do this on your own. You can prove that Vj over V is also Nj over Nt equal Yj. So the summary equation here is that Yj is equal to Nj over Nt equal Pj over P equal Vj over V. And that is a very important equation. I'll put lots of stars around it to mean it's very important. And this is for an ideal gas mixture. So that is a very important equation that you'll be using a lot. Now let's do a very quick example problem, and you'll have something similar in your quiz. So we're given 3 chemicals, a natural gas mixture. For natural gas here, these are all ideal gases. Natural gas that you burn for heat is pretty close to this. It depends on the company. They also add some odor that you can smell, like that rotten eggs, but that's a very small amount. But roughly 90% methane, 8% ethane, ethane, some people say, and propane 2%. So we have the temperature and the pressure also. Calculate the partial pressure of the propane in this mixture in kPa. So from the propane, Yj is 2%, which is 0.02. If you want to write it in ppm, you can write it that way. And then Yj equal Pj over P. That's from this equation I just showed you. So I'm going to put P instead of J. So this is the propane that we're talking about. We want to solve for the partial pressure of the propane, which I'm calling PP. So PP is simply equal to Yp times P. So that's our answer. And putting in the numbers, PP is Yj, Yp here. And remember, you don't put ppm, you put in the actual number. You don't put percent, put in the number, which is 0.02, times the total pressure, 445 kPa. The units are exactly what we want in kPa. So this turns out to be 8.90 kPa. So that's our answer. So I repeated this for the methane and the ethane, and I get 400.5 and 35.6 kPa. And I just wanted to show you that if you sum these, we get 445 kPa, which is the total pressure as it has to be. So what we've done is we've just proven Dalton's law. So I'll stop there and enjoy the quiz. I think some of these first quizzes are pretty easy, but you'll get in the habit of taking a quiz every time you do one of these lectures. Thank you for watching this video. Please subscribe to my YouTube channel for more videos.